Alright. So good morning everybody. Mehmet and Chen. Missing. How are you today?
He's also missing.
He's also missing. Dimitri, are you with us? How are you? Sad? Don't worry. All is well. Okay. We are going to remember first what we did last time. At the end of last lesson, we were talking about charge carriers, right?
Yes.
Okay. Let's watch this short video to remember what we have learned about charge carriers, and then I will tell you what we are going to learn today.
Electric current is the net flow of electric charge carriers from one point to another. The charge carriers can be negative, positive, or a combination of the two. Which is the case is not a concern for most applications. For this reason, scientists have chosen to treat most electric currents as if they were entirely due to the movement of positive charges. This equivalent current is referred to as conventional current. For many applications, it is not important whether the negative charge carriers are moving in one direction or the positive charge carriers are moving in the opposite direction. In these cases, scientists treat electric current as if it were entirely due to the movement of positive charges. The
Conventional current
conventional
direction.
current is a current that has the same net movement of positive charge as the actual current. In the case of a current within a metal, the actual current is due entirely to the movement of negatively charged electrons.
In metals, we
If
have
the
electrons.
electrons, which are negatively charged, move from right to left, the conventional current is an equal amount of positive charge moving from left to right.
Right?
In particle accelerators, currents can consist entirely of moving protons. In this case, the conventional current is the same as the actual current. In some gases and dissolved salts, current can be due to positive charges moving to the right and negative charges moving in the opposite direction. In this case, the conventional current would consist of positive charges of an amount equal to the total movement of charge, but all moving to the right.
So in each case, we only look at the direction of the possible positive charge in the circuit, whatever it is. In the case of the metals, we have many free electrons. Electrons move, let's say, from left to right, but conventional current direction is represented by right to left direction, right? In the second case, let's say in particle accelerators in cell laboratories, you know that, right? We're looking for the Higgs boson, the God's particle it's called. In that experiment with the large particle accelerator, they have protons. And in that case, of course, the conventional current direction is in the same direction with the direction of the protons. In the last case, third case, we have both of the ions, positive and negative, and you still consider the direction of total charge, positive charge, in that way. Okay, this is what we have just talked about at the end of the last lesson. And we have actually defined charge and current in relation with time. What was the equation? Can you remind me? Nobody else? Nisa? How can we define current?
Q equals IT.
Q equals IT. Charge equals current times time. Or in other words, current equals charge over time. Right? In symbols, I equals Q over T. This was the equation we have learned in the last lesson. And you had a homework, yes?
For the number of electrons, like the electron charge, what is charge divided by electron charge?
If you are looking for the total number of electrons, okay, then you can just divide the total charge by the charge of one electron, which is 1.6 times 10 to the power of minus 19. This will give you the amount of the number of electrons.
And when do I divide current by electron charge?
Current by electric charge?
Yeah.
You don't. No, you divide charge by
In the
the total.
question,
We will have a look. Okay, I will. Can you show me your work, what you did?
Yes.
Okay, question numbers 3 to 7. Alright? You have them?
yeah, I had a problem with that also.
Is that?
I see. I thought something like this. This is wrong.
Very good. Very good. Okay.
So if you look 3, 4, 5, 6, because this one has. Yeah,
Yes.
there's a problem. Yeah, there is.
There was a kind of drift velocity formula. That one you are looking for? This one. Was it about the speed?
No,
No.
it was something. It's 5.
I don't know.
It was the number of electrons per second.
Per second passing. Okay, if you are looking for number of electrons per second in unit time passing, then you have to divide by time as well. So you actually get the current there, right? Current is charge per second, right? Charge, coulombs per second. So if you know number of electrons per second, you have to divide this number by the time, given time amount. Alright? You have to just divide it by time. Good. Mehmet, you were absent last time. You should take the notes. Okay. You should write the units. Oh, actually, it was a number of electrons, so you write electron. Alright. Any question you want to ask me from the homework? 3 is easy. 4 is the same calculation with different time units. Milliseconds, minutes, and so on.
4, 5, C
5C.
and 6, because for one of them we used I,
Yeah.
current, and for the other one we used Q to find the number of electrons. Why does this change?
No, in the last part, C, it says number of electrons per second passing. So it's not only the number of electrons. If they ask you only the number of electrons, you divide charge by time, by the charge of electron. Total charge divided by the charge of one electron. If they ask you number of electrons per second, then you have to divide also this number by the total time, which is 50 seconds given in the problem. Okay? How many electrons pass? This is the total number of electrons, and how many electrons pass in every second. So you have to divide this total number of electrons by 50 seconds. You get charge number of electrons per each second. Okay? Alright, so we are going to continue today with the point we have just left last time. I told you that we are going to talk about the human brain a little bit, because it's all related with those charge carriers and current electricity. In general, we can say our human body is a kind of electrical machine. It works with electricity. All your 5 sensors, I told you last time, right? There were different sensors in our body. Even 5 different sensors under your skin, for pressure, for hot, for cold, for pain receptors. We have different sensors which take a physical stimulus from outside world and change it into what? What do sensors change the physical stimulus into? Into what do they? Into electrical pulses, into electrical signals, right? And where do they all signals go? I touch. goes through your nervous system to your brain. And what happens inside your brain? Myth says only 10% of our brain we use. Actually, it's a myth. It's not. It's busted by the Mythbuster. Did you watch it? Some of us probably use less. It says, of course, you know this character already. Yeah, Simpsons. I like that cartoon. The human brain is made up of neuron cells. Neurons are really extraordinary pieces of electrical devices, let's say. They do something amazing. There are millions of connections between neuron cells, and each signal knows where to go. And this is obvious in your childhood. Scientists try to understand what happens in your brain and how those neurons find connections with each other. And I just found this video, which is really interesting, about the communication between neuron cells and the human brain. Let's watch.
Billions of brain cells are not done forging links with billions of other brain cells. Eventually, there will be trillions and trillions of connections between cells.
Trillions of
Charged
connections, you see?
electrical pulses rippling like lightning storms across the hills and valleys of the brain's deeply furrowed tissue. Every cell in its place, every link between cells carefully organized. Nothing random, nothing arbitrary.
What we would really love to understand is how the brain, during development, generates millions and millions of neurons, sends them to the right position in the brain, and then somehow instructs each of those individual nerve cells to form very, very specific connections with one another. You can think about development like a play that follows a script that is written down by the genetic code, but it has no director, it has no producer, and it has a bunch of actors that have never spoken their lines before. Despite all this, you pulled the play off. To me, that's a miracle.
Right. Imagine the network system of school, even the whole city. Thousands of millions of connections, right? The whole network and electricity grid of the whole city. If there is a mistake somewhere, right? You call your mom, somebody else will go on the other line, right? It doesn't work. If there's a disturbance somewhere, if there is a misconnection anywhere in the system, you just fail. But it doesn't happen in the case of human brain. All those neurons with millions of connections, they actually know where to go. And it works really in a very well designed way. Yeah?
Is the camera recording?
Yes? And then? Okay. So, how does it happen? How does does a neuron communicate with other neurons? How does this electric signal transmit it to the other cells? This is all about action potential. Action potential, it's called. I want to just show you how neurons look like and where we can get a kind of electric circuit here. Alright, this is a neuron. It's not our subject right now to study the structure of the neuron, but you just need to know that it has an axon site here, and this is the cell body. I will skip this part quickly. And this is where we have all the connections are made and transmitted to the other neuron cells. So, remember the charge carriers I told you about. There are positive charges in the membrane of a neuron. These are sodium and potassium ions. Sodium ions are distributed above and potassium ions are at the lower part of the neurons. If you measure the potential difference because of this charge distribution, you will see at the rest case, when the ions are at the resting potential, you have minus 70 millivolts. That's the resting potential of the neurons. There are different gates for each ion, special. Potassium ions can pass through only potassium gates. Sodium ions are allowed to go down through the sodium gates. And because of this charge transmission passing from inside to outside, you have a kind of depolarization. A potential difference is produced. Look. The difference, of course, because of the charge separation, we have a difference measured in voltage. And when you change this charge distribution, ions on the inside of the axon relative to the outside of the axon, we have this pulse traveling through the neurons. Look, outside, inside. Gates are opened, sodium ions are going down, changing the positive distribution here. Potassium ions are going up. So this happens in a very fast way. This polarization produces the electric pulse to be generated, just like that. Voltage is increased and then decreased. Of course, this is a very complex mechanism which we cannot just talk in a few words like that. And it really looks like a circuit with resistor and a capacitor if you investigate. I'm not going to talk about in detail of this system. We just need to know maybe here that this charge distribution, because of the potassium and sodium ions, produce the electric signal, the current, the pulse, travel through the neuron just like that. Okay.
Why does it give out less than what it takes in?
What does it what?
It takes in more than it gives out.
Because of the charge. If the same amount of charge goes in and same amount of charge goes out, then you will have still zero, resting potential. So 3 positive sodium ions going down, 2 potassium ions going up. Because of that charge
And that
difference,
gives the
you have the pulse. You have the potential difference. Otherwise, you will have the same resting potential. In order to have the potential difference, you need to change the ions distribution. Yeah? So, this is a really cool thing actually. It happens in every single millisecond of our life. Right? When you see something, when you touch, when you taste, when you hear, when you smell, when you talk, in any function of our body, this happens simultaneously in all neurons of your brain, of billions of connections. They all transmit the signal like that, and it works in an instant, and we don't really feel what's going on inside. So the output is perfect. Alright, let's go on. Do you know this guy? Battery Man. Battery Man. This guy is an extraordinary human. We usually, we are all affected, not usually, all the time, always, we are affected by the electricity, right? If you put your fingers in 220 volts, what will happen? You will die. But this guy lights a bulb. Look. It is from trailer of a documentary. his friend with electricity. Look at that.
I wish it had one.
Never try this at home. I think he's Serbian. They all hold their hands. The best part is he can control that current. Whenever he wants, he produces that pulse.
Moj ćale nije strog, a sve mi ispunjava.
Ljudi su čuli o meni, gledali me na televiziju i onda drago mu je da se sretne sa mnom, ali uz strah da mi pruži ruku. Nemoj da se plašiš, od mene kupi zimi, bit će dobro. Putujem iz Gradovna i položim ljudima migrena, glavobolja, sinusi, problemi sa
Akupunktur.
trudim se 50-50. Bilo bi loše kad bismo rekli ja mogu sve. Sad ćemo mi da vidimo šta ti sanjaš noću. Može? Ajde, da vidimo šta ona sanja noću. Evo ga.
What could be the other side in her hand holding? Did you see?
Velika struja je mašta.
There was a metal holding.
Koje ću moći da pokažem svetu. San je treći Guinnessov rekord. Mora da padne. Dva ih imam, mora i treći. Milion volti, da mi se napravi trafo. Na njemu ću da pokušam da se napunim i da 5 žica bude glase.
Because he does that, imagine. He's not normal.
Why does he do it? It harms him.
He doesn't harm himself. No, there's no effect on himself. Of course, this is nothing we can explain. Basic science. It's something different. But we all have some electricity because we are all some conductors, people. This is an extraordinary example, of course, is an exception, but we all conduct electricity. And we might be all like a battery. I can prove that. All you need is 2 different metals. One aluminium, and another one is copper. And I'm going to connect these two to the voltmeter. Alright? We are going to connect one terminal of the voltmeter to aluminium plate and other end of the voltmeter to the copper plate. Okay. I will adjust this to something like, okay, millivolts. Millivolts.
Does it hurt?
And no. Can you see?
Should I hold it?
Hold it to your friends. Alright. I'm just going to hold 2 metals. What does it show?
638.
Yes. I'm now generating 640 millivolts by just holding these 2 different metals in my hand.
I think
I'm like a human battery. How? Maybe you have more. Let's try. Take it out.
You had 640.
Oh, yes, you have more. 650. He's very stressed today. Maybe he has more. Let's see. I told you. 733 millivolts. Very good.
How much did I have?
650. What about you guys? Try. Okay. Augie has even less than. Oh, I'm increasing. You can control it. 700 720, well still 720 millivolts. What might be the reason? We are not batteries, we don't hold batteries in our fingers, but still it measures some millivolts of voltage potential difference. Yeah.
Didn't we see a diagram like potassium
Huh.
and sodium?
Sodium.
They move.
Yeah. So
And-
there must be a charge
Yeah,
movement.
Charge
Yeah. What
movement.
charge moves from where to where here in this case?
from our brains to from our light charging.
These are two conductors. They don't really touch to your brain. They touch to your hand. What we have in our hand.
Veins.
Huh?
Veins.
Okay, but what we have at the surface of your skin?
Sweat.
Receptors.
Sweat. Yeah. And what is it made up of?
Oh.
Isn't it something like a chemical, an acidic substance? Huh?
Minerals.
I don't know. Huh?
Minerals. Salt.
Minerals, salt. Yeah, it's like salty water. It's with minerals. There are some ions in your sweat, in your hand. And when you touch copper, because of that chemical reaction between your sweat in your hand and the metal, you transfer electrons. You take electrons from the copper. Electrons are transferred from the metal to your hand, between the interface of the metal and your hand, due to that salty water that you have in your hand.
But if you
And what happens to those electrons? They go to the other side through your body and they give those electrons to the aluminum. Electrons are taken from the copper plate and transmitted to the aluminum plate. Circuit is completed and we have a potential difference. Very small potential difference because human body has a high resistance actually. We can measure our own resistance as well. This resistance actually, because of the body tissues we have, is actually decreasing the total amount. Yeah.
What if you're touching the ground at the same time, like outside? Does it
Then you will
decrease-
transfer those electrons to the ground.
Does it
If I
decrease
don't, no, if I just hold here this one and touch somewhere else to another metal, of course, since the electrons,
it? No, let's say you're standing with your,
Uh-huh.
bare feet.
it
on
will
the
be
ground
less. Some electrons will be grounded and this amount will be less. Okay? The voltage you have generated will be less. Okay, so this is a very good example of potential difference that we have just observed in human battery. That's called human battery. If we had a larger plate and put all our hands like this, it would be actually maybe better than this. Alright. Again, as I said, this is the explanation of the human battery. If we try with different metals, we can get different results. It could be a nice science fair project actually to obtain the maximum amount of potential difference by the human battery. What metals you need to use, what surface area, does it matter, as we have seen actually, from one person to another and so on. It's like electrolytes. Your fingers are like electrolytes in electrolysis experiment you have done in chemistry lessons. Okay, now today we are going to learn something new. Potential difference is our subject. Please write down your title. The objectives of today's lesson. New subject.
Okay, I have to read some.
We will define potential difference and the volt. You already know in general from secondary school and your last year IGCSE course. You have used volts in many problems so far, maybe last year, and you use it in everyday life. When you buy a battery or when you have an electric device out of battery, you supply some voltage in order to make it work. Standard battery is 1.5 volts, as you know, written on them. And we are going to learn what this potential difference or voltage means. And we are going to recall and solve problems using voltage equals energy over charge. So work done or energy over charge. is equal to voltage. Okay. To understand this, I have a very nice analogy. First of all, I want to show you that. Look at here. We can think of an electric circuit like a flow of water in a system like this. If you look carefully, in a normal electric circuit, we have a power source and a kind of consumer, like a bulb. There's a switch or other resistors and so on, but that's the simplest case. A power source and a light bulb. What are those things in between moving around? Electrons. If I connect these two with metal wires, electrons, free electrons, start to move from one side to the other side, and that's the current electricity. When they come to the light bulb, those electrons give off their energy, and electrical energy that they gain from the battery turns into light energy. Yeah.
If the electrons are moving up, shouldn't the current be the other way around?
Yeah, actually, if the electron, this is not the current direction, electron flow this way, then the current, conventional current direction, is in the other way around. We're just looking here at the electron flow. Now, this really looks like a water pump, alright, a pump pushing water by applying pressure to water, and the water moves from the upper tank to the lower tank, and the cycle continues like that. And in between here, I have a turbine. This turbine turns, gets its motion because of the movement of water, just like a windmill. A turbine of a power station, same method. The pump pushes the water up, water turns the turbine and goes back to the lower tank, and then the cycle repeats itself. Now the water in this circuit looks like what in the electric circuit? Electrons, yeah. Electrons are like the water particles moving around. The turbine is like
The light bulb.
the light bulb. Spends the energy of the water. The water, gravitational potential, kinetic energy of water turns into the kinetic energy of the turbine. Electrical energy of the electrons turn into light energy of the bulb, right? And the pump gives energy to water. Power supply battery gives energy to electrons. So the pump looks like the battery, right? I have a simple circuit here. The battery provides energy to the electrons in the complete circuit. In order the current to run, you need to have a loop, a complete circuit. If the connection is not done, like in this case, no current flows, no light. When I switch it on, light is lit. Because metals are now all connecting with each other, there is a complete circuit, a simple circuit, and the electrons transfer their energy to the light bulb, right? And this produces heat and light from the electricity. The battery provides potential difference, we say. Now you can tell me, now you can guess, people, how can I define the potential difference or the voltage provided by the cells? I have one cell, 1.5 volts. Total battery is 3 cells. How much is the total potential difference? 4.5 volts. 4.5 volts of potential difference, the voltage provided by the cell, or in other words we call EMF, electromotive force of the cell, is actually equal to the total amount of energy given to each coulomb of charge in the circuit. Okay, let's write this down. Let's write this down. Alright, if you have a simple circuit, write it down. Defining potential difference in a simple circuit. Here is the battery. Here is the bulb. Okay? Let's say the battery provides 4.5 volts, just like in the same case we had in the experiment, the demonstration here. And this 4.5 volts of power supply provided by the cell tells us that 4.5 joules of energy is given, pay attention, to each coulomb of charge. Every single coulomb of charge in the circuit receives 4.5 joules of energy. Yes?
Which one is the positive part in the battery? The short
The
one?
longer one, of course. It's a positive, isn't it? 4.5 joules of energy is given, write it down, to each coulomb of charge. This is the potential difference across the bulb. So 4.5 joules of energy is transferred into light through the light bulb. So potential difference represented with PD is equal to energy transferred represented with W divided by charge Q. In symbols, voltage energy over charge. Of course, we can write the units: joules, coulomb, and volts. This is V for the symbol, and this is for volts. Is also V. In some textbooks, you can see this as U, not to confuse with the symbol and its unit. Sometimes they use U in terms of V. How much energy transferred for each coulomb of charge? That's the potential difference. Any question? Everything is clear? Good. That's why if I remove one of the batteries here, give a look, I obtain this amount of light from the cell, right? From 3 cells. If I just skip one of the cells and put 2 cells, did it change?
Less intensity.
Less intensity. Less energy is transferred. Because I provide less potential difference. Less energy given to each coulomb of charge because of the less potential difference. Only 3 volts now I apply, so I have less brightness. If I just give one cell, what happened? A very little amount of light. Less energy is transferred by 1.5 volts of battery. In this case, every coulomb of charge is getting 1.5 joules of energy. In this case, every coulomb of charge gets 3 joules of energy. And in this case, every coulomb of charge gets 4.5 joules of energy. Okay? Every coulomb of charge. Does it mean every electron? Huh? Every coulomb of charge doesn't mean every electron. Because one electron has how much charge?
1.6 times 10 to the power minus 19.
10 to the power minus 19 coulomb. Imagine, 1 coulomb is a very big amount of charge. How many electrons will make 1 coulomb of charge?
Like 6
A lot.
times 10 to the power.
6 million, 10 to the power of 18. This number of electrons will come together to make 1 coulomb of charge. Alright? If I say 4.5 joules of energy is given to each coulomb, I mean 4.5 joules of total energy is given to 6 million of electrons. Not only one single electron. Be careful about it. Alright, we have just defined that. I want you to write your homework. Page number 205, 9 to 12. 9 to 12 is your homework. Okay? And from the worksheet I gave you last time, I want you to now look at question number 11. 11. And tell me how we can calculate that. Question number 11 in the worksheet. Let's solve one problem. You already know your homework now, and I will give you also a very interesting project assignment at the end, and we'll finish the lesson. Let's solve one problem at least. Calculate the potential difference across a component that transfers 15 joules. Yes, what's that 15 joule? W, right? We have 15 joules of energy provided in a component. And charge flows how much? 4.2 coulombs. And what's the question? Calculate what? Calculate potential difference. What is voltage? Yes. 15 over 4.2. Voltage is 15 joules over 4.2 coulombs. And how much is that?
3.57
3.57 what?
volts.
Volts. How can I write it in two significant figures? Because there are two significant figures in the list number given. 3.6 volts. Alright. Easy. We have, as I told you, electricity is not only in our body, it's everywhere, in the circuits, in nature, in animals. Animals utilize electricity as well. Have you heard about this fish, electric fish? What does it do? Electric eel. Yeah, what does it do? Uses electricity to do what? To hunt, to find, to kill its prey. And how much voltage does it generate? Do you know? A lot. Huh?
So it's only effective at a short distance.
Short distance, but still it's such a fish, such an animal, producing 500 watts of power. A shock, electric shock up to 500 volts. I want you to write this down, to Google this. Okay, search some extra information about this fish and present it to me next time in the lesson. Tomorrow we have a lesson. How does this fish produce this electricity? How its mechanism made to work? Where and when does the fish use this ability? What makes this electric eel unique, different than other animals? And maybe the most important question, how could we use this? How could engineers use this technology in electric eel to develop new ways to power small electrical devices? It's acting in a short range. Imagine this fish generates such a huge power all the time. It has. Imagine we had the same technology in our mobile phones. There wouldn't be any battery problem, right? So think about those stuff as well and tell me some
So
ideas.
do we have a lesson after school today?
Yes, we have. So before we go, let's revise what we have learned today. All right. I'm going to see you after school for the extra lesson today. Let's summarize. We have learned, first of all, you have remembered charge carriers, right? Can be positive, negative, or both in each case. And you have learned how brain works, how neurons transmit their signal. We have just remembered the equation from the last lesson. What was it again? Q equals IT, don't forget. And we have just learned one more equation about potential difference. And what is it? Energy over charge. And if you know the amount of energy and the charge, you can find voltage. And last thing, how can we define potential difference? In words, the amount of energy given to each coulomb of charge. Very good. Okay. That's all for today. Have a nice day. And please do your homework. I will check it.